Quadratic solutions. Our objective here, determine the nature of quadratic solutions, including how the solutions look on the graph. Which reminds me, I should get my calculator ready. I am ready, good. Okay, so what do we know? Well, we know what a quadratic equation is, or a quadratic function. Any equation that can be written as ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a is not equal to 0. In other words, you must have a squared term. Ax squared plus bx plus c equals 0 is called the standard form of a quadratic. We know that all quadratics are solved by setting them equal to 0. We know what an x-intercept is. It is where the graph crosses or touches the x-axis. And we know that the letter I is equal to the square root of -1, which introduces us to the imaginary or the complex number system. All right, let's put those things to use here. Give me a second to get, there we go. All right. A quadratic is a degree 2 polynomial. Every degree 2 polynomial has 2 solutions. And those solutions are called roots, or they're called zeros. As we get further into the course, we'll be primarily calling them zeros. But when it comes to polynomials, solutions, roots, zeros all mean the same thing. And every polynomial, every degree 2 polynomial has 2 solutions, as long as we count the multiple solutions separately, and we'll see how that looks. Okay, what are our possibilities for solutions when it comes to quadratics? Well, we could have 2 real number solutions. Graphically, because they're real numbers, we have 2 x-intercepts and they will be crossed. Each will be crossed in this case. We could have 1 real number solution that occurs twice. Again, as long as we count multiple solutions separately, we can call this 2. Graphically, we're going to have 1 x-intercept that is touched. Let's remind ourselves that real numbers are numbers that appear on the number line. Therefore, real number solutions will either touch or cross the x-axis. They are x-intercepts. And our third possibility for solutions, we could have 2 non-real or 2 imaginary solutions. Graphically, the graph is not going to touch the x-axis at all. There are no x-intercepts when we're dealing with imaginary solutions. Imaginary numbers on an xy graph do not touch the x-axis. Okay, let's do some solving. Get my paper together here. I think I'm somewhat straight. Find and define the solutions of 2x squared equals 1 minus x. Well, how do we solve a quadratic? We know it's a quadratic because the highest degree is a 2. We set it equal to 0. So 2x squared plus x minus 1 equals 0. Now we can choose to use the quadratic formula, or we can choose to factor this. I made the problem, of course. I know it's factorable. I know that 2x squared is only 2x times x, so I know my first terms are 2x and x. I need a 1 in the back, so I have a 1 and a 1. I need a positive x, so it's positive 1 back here and a minus 1 here. And now I can use the zero product property. If a times b equals 0, then either a equals 0 or b equals 0. Solving this, x is equal to 1/2 and x is equal to -1. So in this quadratic, I have 2 real number solutions. 2 real number solutions. 2 real number solutions, okay? That's what I got there. I got two real number solutions. I'm going to graph y equals 2x squared plus x minus 1. And we're going to see that we have two x-intercepts. Put this up here for you. Let's go to the graph, y equals. Let's put in 2x squared plus x minus 1. 2x squared plus x minus 1. I think I'm in the standard window, but just in case, I'll zoom 6 to get to the standard window. Here comes my quadratic, which graphs as a parabola. And you can see I have two x-intercepts. And if we want to go in there and see what they are, well, first off, I'll zoom in a touch. Get a little clearer look at where they are. Here they come. Here comes the graph. Okay, so I've got one over here that looks to be at -1, and this one looks to be at between 0 and 1, right around a half. Let's go to calc our 0 on the left side. We'll bound it. And then press enter. There's our -1, which we have right here. And we'll go to the one on the right side, second calc, the 0, and I'll bound it. Okay, and there is the positive 1/2 right there. Okay, so I graphed it. And indeed, I have two real number solutions. I have two x-intercepts. And as we know from our real number solutions, the x-intercepts are crossed. If you look here, both these x-intercepts, the graph crosses at those values. Okay, let's take a look at another example. I think we've got ourselves set. Find and define the solutions of x squared plus 25x equals 10x. Well, it's a quadratic. Its degree 2 is the highest degree. We solve a quadratic by setting it equal to 0. Into its standard form, sometimes also called the general form. Okay. Now, this one we can again solve with the quadratic formula. It is also factorable. It factors into x minus 5 times x minus 5. And now I'm going to use the zero product property. If a times b equals 0, then a equals 0. Or b equals 0. And this one solves as x equals 5, and this one solves as x equals 5. Well, we have two solutions. Okay, as long as we count multiple solutions separately, I have a 5 and a 5. So I have one real solution that occurs twice. Okay, so I have one real solution. If I spell that occurs twice. And if we count them separately, that's 2. Remember, every degree 2 polynomial, every quadratic has two solutions if you count multiple solutions twice. Okay, so now let's graph it. Let's graph this. Y equals x squared minus 10x plus 25. And let's take a look. So we'll go into here, we'll go into y equals, whoops, y equals, oh, I'm in the wrong place, clear, y equals, and I'm gonna graph this quadratic, x squared minus 10x plus 25. Whoops, I forgot to zoom standard. We're not even gonna see the graph, I don't think. Nope, didn't even show up. Let's go back to the standard window, because it needs to show up for us. There it is right there, off in quadrant number 1. And you can see I have an x-intercept, but the graph does not cross it. The graph just touches it, and actually it turns around. Where is that 0? Okay, let's go to second calc. The 0, I'll go down to the left side and bound it on the left and the right. There we go, and press enter. And there's your 0 right there at 5. I'm not so sure why it wants to show me 31 millionths, but that's the little extraneous, something going on with the software there. But the 0 is at 5, which we knew. Okay, so we have one x-intercept at x equals 5. Again, notice that the graph hit it and bounced off. We'll learn more about that later as well. Okay, finally, let's look at a third example where we have imaginary, non-real solutions, roots, or zeros, okay? So let's see here. Find and define the solutions of x squared minus 4x plus 29 equals 0. Okay, that's already said equal to 0. I'm just going to write it again. Okay, so this one, I happen to know it is not factorable. But you could try, 29. Unfortunately, 29, though, is a prime number. There's no way to factor 29 to get a 4 out of that. So let's use our quadratic formula. X is equal to opposite b, which is 4, plus or minus the square root. B squared is 16, minus 4 times A is 1, times C is 29. All over 2 times A, which is 2. Okay, well, I'm going to require a calculator. I'm going to go ahead and solve what's under here, under the radical called the radicand. And I'll pull out my calculator to do that. And out comes negative 100. 16 minus this whole thing is negative 100. Okay, my radical is a negative. This is putting me into the imaginary land, into complex numbers. Let's remind ourselves how we simplify a quadratic. A root. This is equal to the square root of negative 1 times 100. And this, of course, this is I, and this is 10. So that simplifies to 10i. So let's rewrite that. X equals 4 plus or minus 10i over 2. This is a common denominator. Okay, the 2 goes to both the 4 and the 10i. And so I'm going to come up with the answer. 4 divided by 2 is 2, plus or minus 10i divided by 2 is 5i. So I have two solutions. Of course, I always have two solutions when I deal with quadratics. 2 plus 5i and 2 minus 5i. By the way, these are called an imaginary conjugate, a word you may have seen before. Pair. Conjugate simply means we have the same outside terms with the opposite sign between them. Those are conjugates. The same things on the outsides, the opposite sign in between. And they always come in pairs, by the way. Okay, so what do I have? I have two imaginary, non-real, struggling to spell the word real, it seems like, for some reason. Two imaginary non-real solutions. Okay? All right, so again, I always have two solutions. So let's graph. Y equals x squared minus 4x plus 29. I have two solutions. They're both imaginary. They're both not real, which should tell us that they're not going to be x-intercepts. All right, they're not real, so they should not show up on the graph on the x-axis. Let's take a look. Oh, my battery is low. Okay, recommends I charge it. I'll do that shortly. Hopefully it works for this. Okay, x squared minus 4x plus 29. Let's make sure I'm in the standard window this time. Here comes the graph. Do I even see it? It's not going to touch the x-axis. I don't. It's not in my negative 10 to 10 window. So I'm going to zoom out. And let's see if I can find it. I'll zoom out from the origin. Here it comes. There it is, right up there. It's up high. In this case, it's up above the x-axis. The parabola is opening up, but certainly you can see that there are no x-intercepts. It's way up here above the x-axis, mainly in quadrant number 1, but also in quadrant number 2. Okay, so when I have imaginary or non-real solutions or zeros are not x-intercepts. Whoops, I was going to write the letter Z. So I have no x-intercepts in this case. So there you have it. Some work and looking at how you find solutions of quadratics, also called zeros or roots, and what they look like on the graph.